This is Mr. Nabi from Roger Bacon High School. This video for AP Calculus is on implicit differentiation. So the first question that I'd like us to consider here is, how are y equals x squared and x squared plus y squared equals 9 different? Well, you could look just at the equation itself and say that, well, one variable is squared while the other has two variables that are squared. You might also say that in the first, y and x are on opposite sides, and in the second, x squared plus y squared are on the same side. Well, those are just cosmetic. I could easily move variables to one side or the other, and so on. But the key difference here, from a function perspective, again, from a function perspective, is that this first equation is a function, and the second equation, x squared plus y squared equals 9, is not a function. If we were to graph this first one, it's just a parabola centered at the origin. And if we were to graph the second one, it's a circle with a radius of 3. A radius of 3. So we've got a circle here. And clearly, a circle doesn't pass the vertical line test, so it's not a function. So that answers question number 2. When do we and when do we not use implicit differentiation? The key here is we're going to use implicit differentiation typically when we want to differentiate, we want to find dy dx for equations that are not functions. Equations that aren't functions. Right, there may be other times that that you would do it, but typically, for our purposes, we want to do this implicit differentiation whenever you have an equation that isn't a function, that can't be, essentially when it can't be simplified to y equals something. Okay? So let's talk about how we do this. And I think the best way to talk about it is just to dive right in to point 3 here with some examples. X squared plus y squared equals 9 was the example we started off with, so let's take the derivative. If we take the derivative, we're going to have the derivative of the first term plus the derivative of the second term equals the derivative of the last term. And here we go. Derivative of the first term is 2x times, and we actually have always left something off that I want to put in here at this point, dx dx. We're taking the derivative of x with respect to x, plus the derivative of the second term. Well, that's actually 2y dy dx. We took the derivative of y with respect to x, and the derivative of the constant is always 0, so we can just put 0 there. Now again, derivatives are rates of change, so this term here, dx over dx, is actually what's the rate of change of x with respect to x. Well, as x increases by 1, it's increasing by 1. So essentially this value here, dx over dx, is 1, because x is changing in relationship, in proportional relationship with itself. It's a 1-to-1 rate of change. So this value here, dx over dx, is just 1. We don't typically write it, but I put it here as an idea of taking the derivatives of an equation with respect to a certain variable. So this value here is 1. So we're left with 2x plus 2y dy dx equals 0. Now if I want to know the derivative, I want y prime, and another name for y prime is dy dx. So at this point, I only want you to solve for dy dx. So getting everything that's not dy dx on the other side brings us to 2y dy dx equals negative 2x, and then dividing both sides by 2y gives me the fact that dy dx equals negative 2x over 2y, and this simplifies to negative x over y. So the derivative of this function, this circle, is negative x over y. Okay? Let's try another one. Example number 2 here. X squared plus 3xy plus y squared equals 7. Here we'll take the derivative of the first term, which is 2x dx dx, plus 3 times, and now we actually have a product here. X, y is a product, so I have to take the derivative of the first term. So dx, the derivative of x would just be 1 times y, plus the derivative of the second term, which is dy dx, times the first term, x, and then plus 2y dy dx for the derivative of the third term here. And the derivative of 7 is simply 0, so now we're all set. A reminder, dx over dx is simply 1, so we've got 2x plus, I'll distribute the 3y plus 3x dy dx plus 2y dy dx equals 0. And now we want to solve by getting dy dx's all alone. So what I can do here is bring these two terms to the other side and factor out dy dx from both of those remaining terms. So if I bring these to the other side, that'll be negative 2x minus 3y. And if I take out a dy dx of what's left, I'll have 3x plus 2y left inside there. And finally, if I divide both sides by 3x plus 2y, I've got my final answer, which would be dy dx is negative 2x minus 3y over 3x plus 2y. So there's your derivative using implicit differentiation. Okay. One more example, point number 4. We want to take higher order derivatives. Well, let's go ahead and first of all take the first derivative. So y prime for this red equation here would be 6x squared dx dx, which is 1, so I'll just leave that off, minus 6y dy dx equals 0. Alright, so what I get here is 6x squared equals 6y dy dx. If I divide both sides by 6y, I get x squared over y equals dy dx. This is y prime. Well, if I want the second derivative of this, essentially I want the derivative of the derivative. So to do that, I'll actually have to take the derivative of what I have here, x squared plus y, x squared over y. I have to use the quotient rule. Quotient rule is ho d high minus high d ho over ho ho. So ho d high, so y times the derivative of the high function, 2x, minus high d ho, the high function, times the derivative of the bottom function, which is dy dx, all over the bottom squared. Now you might think you're finished, but at this point we are almost finished. We have dy dx inside of this solution, which we're calling the second derivative. And I can't leave dy dx in there. I know what dy dx is. Dy dx was found in the previous derivative. Dy dx is actually x squared over y. So this can be simplified as 2xy minus x squared times x squared over y all over y squared. Now I've got a fraction inside of a fraction, so I actually want to do a little work to simplify this, to clean this up. So this would be 2xy minus x to the fourth over y. And I'm going to write this as divided by y squared. Now in order to clean this up, we want a common denominator, so this is going to be 2x y squared minus x to the fourth over y. And anytime we do this, we multiply by the reciprocal. So the second derivative would be 2x y squared minus x to the fourth all over y to the third. This would be the final answer. for the second derivative, for y double prime. Okay, implicit differentiation. A couple good examples there. At this point, I'd like you to try from page 167, problems 1 to 3.